Okay lah, I think we can start now. Okay, we are in the chapter on the gas turbine power plant. Okay, we'll start off with a bit of introduction. Then we'll see different types of gas turbine, especially in terms of how do we classify the turbine itself. And then we'll cover a little bit on the thermodynamics point of view, which we have done before in thermodynamics 2, Thermo 2. This is just a repetition for you to refresh back on the equations, especially for the efficiency part. Then we'll see what are the major components necessary for repair and maintenance later on. Okay, and then the performance, how do we assess the efficiency of a gas turbine? Okay, gas turbine variation is on the improvement that we can make to the turbine. There are many types of improvement that we can adopt to our gas turbine power plant. So that is the coverage for this topic. Okay, gas turbine, we have done this before, so this is maybe a little bit in depth in terms of the operations and also maintenance. We know that gas turbine has been there for quite some times. Okay, especially during the war lah. People they introduced the gas turbine for the sake of inventing the jet engine. Okay, that is mainly used in the late 40s. Okay, then only they come out with the idea of adopting the gas turbine in the electricity generation business. Okay, so the main principle is fairly straightforward. You have hot combustion gas is used as a medium. If you can still recall, in steam turbine power plant, they use water as the medium to transfer the energy, right? And then for the gas turbine, now we have air or hot gas, okay, which is used to transfer the energy from one point to the other point. At the end of the day, the energy is actually being converted to the electricity, lah. So you have hot gas as the medium to transform the thermal energy from the heat into the rotating mechanical energy, which is in the rotating shaft for the turbine, which is used to drive the compressor as well as generator. So this is where the conversion of energy takes place. Okay, at present, we know that the gas turbine, it accounts to about 70% of the total generation mix. So that's quite a lot if you consider the overall different types of generation. And then you know that the application, we have many, mainly on the aircraft, the jet engine. We also use gas turbine to produce the electricity. Okay, maybe in some factory, they use the gas turbine for process heat to produce the heat. At the end of the day, what you want in this industry is you want the heat. Okay, at the same time, maybe they use the heat to produce the electricity as well. So we call that a cogeneration plant. Gas turbine also used in the marine propulsion, the ships, okay, and also industries. Okay, this is an illustration for the simple gas turbine system. We have the whole system here comprises of a gas turbine, right? We start off with the compressor on the left-hand side here. And then this compressor is actually coupled with the shaft, which is having the same, the turbine here is having the same shaft as the compressor. And then towards the end here, you have a generator. The principle is fairly straightforward. You have air coming into the compressor. compress the air. You have an increase in pressure, increase in temperature, and then we use the compressed air to our combustor. We got the combustion happen inside our combustor. Hot exhaust gas is used to drive the turbine. Okay, and then the turbine rotate the shaft. The shaft is actually, part of the work is actually used by the compressor, and then the remaining work is used to drive the generator, producing the electricity. So that's how the conversion of energy takes place from the fresh air that comes into the compressor. Okay, this is the gas turbine application. So if you look at the figure on the left here, okay, you have two different types of application for the gas turbine. One for the aircraft engine, right? This is A, and then the bottom one is the application for the power plant. You can see the main configuration are the same. You have compressor, turbine, combustor, the shaft. Okay, and then it's just that how they are utilizing the hot exhaust gas is different. For the case of aircraft engine, you have hot exhaust gas that comes out from the turbine, okay, to rotate the shaft just now. The hot exhaust gas is actually used to create the thrust. Okay, that's why you have to channel that in a nozzle. Okay, nozzle, the function of the nozzle, if you can still recall, is to do the acceleration. So you have the main outcome here, or the main purpose is to obtain the velocity or the thrust. This is where you obtain the jet velocity lah for all aircraft engine. And then on the other hand, for the electricity generation industry, we have the hot exhaust gas is used to drive the generator on the same shaft. Okay, and then the generator is actually the one that produces the electricity. All right, so that is the difference between gas turbine that we use in an aircraft as well as gas turbine for the use of power plant. Okay, this is a simple illustration of gas turbine that they use in an aircraft. Right, usually the gas turbine in an aircraft is much smaller as compared to the one used in the power plant. Of course, because the power required in the aircraft is not as high as compared to the power that is used in the power plant. Okay, the top one here is an example of the jet engine that is used for Pratt Whitney engine. Okay, and then the bottom one is the gas turbine that is used in our power plant, a typical one. I think this model is based on the old GE model. Right, it produces around 55 megawatt, which is quite small. The old one is small as compared to now. Now a gas turbine can produces up to maybe 500 megawatt equivalent of power, which is quite a lot. Okay, for the gas turbine, the construction of a turbine itself is typically compact and also modular. Usually it is much smaller as compared to the steam turbine. And you don't require that many auxiliary system to support the operation of a gas turbine compared to the steam turbine. Remember, in the steam turbine, there are many subsystems required to support the operation of the steam turbine. And because of that, for the gas turbine, it is comparably capital cost is relatively low as compared to the installation of a steam turbine. And then the installation of the gas turbine is fast. Okay, why? Because of its modular construction. Everything, when you buy the gas turbine, they already comes in package or in module. You just need to unpack it and then you do the installation in your power plant. Okay, in terms of fuel, we use natural gas right? And then maybe in some gas turbine, they can also use distillate fuel or maybe gasified coal. Coal, the original coal, they exist as a solid, but actually you can gasify the solid to become a gas lah. Okay, it is called a gas turbine not because it fire on natural gas. Okay, let's continue. Okay, so we have talked about the fuel, and then in terms of the loading, this is also important, right? In terms of the loading, usually we use the gas turbine, if you can still recall, okay, mainly on the peak load, okay, peak load, or maybe in some cases they are used for during the intermediate load, okay, because of I mean, if you want to start up a gas turbine, it is relatively fast as compared to steam turbine lah. So that's why we use that as a peaking load. Okay, the reason is that the fuel that they use in the gas turbine is very much expensive. So we don't want to treat the gas turbine as the base load. Then the capacity is smaller as compared to the steam turbine. Okay, we have many major manufacturer of a gas turbine. Okay, you can have GE, and so you can have ABB, Siemens, and many other players lah for the manufacturer of this gas turbine. Right, this is a typical illustration of the gas turbine module. Okay, and then let's have a look here at the gas turbine general characteristics in terms of their advantages and also disadvantages. This is also important. Okay, in terms of the advantages, you have a short schedule for design, installation, and startup. It means that the time required if you want to purchase a gas turbine for installation is very much faster as compared to the steam turbine. I think the only reason is that there is not many subsystem required, okay, to support the operation of gas turbine. You can buy from the shelf and then you can just run it without having any other system or subsystem or auxiliary system to support the operation. That's why it says here it is scheduled. I mean, the schedule of installation is very short and also very fast starting and also loading for the gas turbine. Okay, this is one of the advantages lah. Gas turbine has lower pollutant emission in the sense that they don't produce any particulate matter, they don't produce any sulfur dioxide, they don't produce any nitrous oxide and whatnot as compared to the steam turbine, especially the steam turbine that is driven by coal combustion. Okay, you compare the fuel used in the gas turbine, we use natural gas, You compare a typical steam turbine operation, maybe they are using coal. Okay, of course, the gas turbine doesn't produce that much pollutant as compared to the steam turbine. That's why they say it is lower pollutant emission. However, bear in mind that since gas turbine is using the natural gas, okay, natural gas carbon-based fuel, the amount of carbon dioxide is still a lot. The amount of CO2 is still a lot as compared to the others because they are using hydrocarbon fuel. So lower pollutant emission here, it refer to the other types of pollutant, not CO2. They are referring to NOx, they are referring to sulfur dioxide, particulate matter, they are referring to the ash as well. So that's why we can say it is actually lower in the pollutant emission. Lower installation costs. This is in relative to the installation of a steam turbine. The cost for the steam turbine is more as compared to the gas turbine. But I think the overall cost, if you want to buy the gas turbine for a power plant, is still expensive lah, in the range of million lah. Okay, it is more compact in size, much smaller as compared to the steam turbine. We have cleaner fuel source, okay, because they are not firing coal, they are firing clean fuel. Clean fuel, you can say natural gas or distillate fuel. No ash disposal, so we don't have any supporting system to treat the ash, and also less fuel handling lah. Remember, if when we cover the topics on fuel and combustion, okay, natural gas, you want to handle the fuel is very much simpler because the fuel that comes to the station, it goes through a piping system. The infrastructure would be, I mean, they are normally there. You don't have any logistic issue lah, especially when in terms of the handling of the fuel. Okay, in terms of the disadvantages, okay, the fuel is expensive. Okay, natural gas is much expensive as compared to the coal. So you can see that the higher fuel costs, natural gas distillate, and therefore it is higher in the operating cost. This is one of the reasons why we don't treat gas turbine as our base load. Okay, we treat gas turbine usually for our peaking load. Peaking load, they don't use 24 hours per day. They might be using a few hours per day during the peak time. Okay, the second disadvantages, since natural gas, the amount of natural gas that we have is not certain, maybe it's depleting at the moment. So we have uncertain long-term fuel supply. We don't know when it is going to last. So it is very limited in terms of reserve. Okay, in comparison to the coal, we have plenty of coal, still plenty now. But then for gas, we are not sure whether it will last for how many years more. And then the output is more dependent on the ambient temperature. Okay, this is very critical. If you want to operate a gas turbine, the exhaust gas or the ambient temperature play a significant role in determining the efficiency of our gas turbine. So the ambient condition means let's say, for example, we are looking at the Malaysian point of view. During the day, the temperature of the ambient can go up to 36, let's say 36 degrees Celsius. During the night, if you want to operate the gas turbine, the temperature, let's say, is around 27 degrees Celsius. So I can say that during the day, the efficiency of my gas turbine is very much less as compared to the efficiency at night because of the ambient temperature. So the efficiency varies according to this temperature. It's very difficult to control, but later on, I mean, at the end, towards the end of the chapter, later on, we will look at this in detail. How does the temperature of the ambient it affects the efficiency of our gas turbine. Okay, and then for the gas turbine, usually the maintenance cost is higher as compared to steam turbine lah per kilowatt hour of energy. I think this is mainly due to the technology lah. I mean, for that particular machine, then the cost, because the cost of producing electricity from the gas turbine, it might be uh, expensive lah because of the fuel price. Okay. Okay, let's have a look here on the two types of power plant that we have. When you talk about gas turbine power plant in Malaysia, we have, under the gas turbine too, we have another two types of plant which utilize the gas turbine. One is the open cycle, the other one is the combined cycle. Okay, open cycle, it is very simple. The most simple configuration. Okay, how does it work? You have fresh air coming into the compressor, compress the air into the combustion chamber. You have combustion run. I mean combustion gas. It drive the gas turbine, and then the exhaust gas we just release it to the atmosphere, to the ambient through chimney. So this is the principal operation of an open cycle. Okay, and then for an open cycle, we usually adopt the plan, okay, open cycle gas turbine only during the peaking load. So if you look at the peaking load requirement in Malaysia, the total hours that they use is less than 2,000 hours per year. So you can divide it per day, maybe less than only, I mean, they only use the gas turbine for a few hours per day just for topping up the requirement during the peak load. Okay, so this is open cycle. And then you can also use the gas turbine for a combined cycle. Combined cycle power plant still have a gas turbine. At the same time, they are using the steam turbine to produce the electricity as well. So you have two works lah. One, okay, if you look at this diagram, the top one is actually the gas turbine system. The bottom one is the steam turbine system. Okay. If you look at this previous slide, remember in an open cycle gas turbine, after the gas turbine, okay, the exhaust gas is actually released to the ambient. And this exhaust gas, let's say for example, we have methane combustion, natural gas. Methane combustion, the maximum temperature is around 1,000 or 2,000 Kelvin, 1,900 degrees Celsius as an example. And then that 1,900 degrees Celsius hot air is actually used to drive the turbine. Maybe after the energy has been converted, the exhaust gas temperature should be around 400 degrees Celsius, 500 degrees Celsius. You imagine gas at 400 degrees Celsius to 500 degrees Celsius, they still contain a lot of energy. So rather than wasting that energy to the atmosphere, they use that energy to heat up water, convert it into superheated steam, and drive the steam turbine. So that's why we come up with the combined cycle. You have a steam turbine cycle at the bottom, gas turbine cycle at the top from this diagram. So in this diagram, the hot exhaust gas that goes from the gas turbine is channeled into a steam generator. Okay, this is something like boiler. But our boiler here, it doesn't require any fuel because they don't have combustion, but they simply use the hot air from the gas turbine, okay, to heat up water. So you have a cycle for the steam turbine here. So in this case, we have two generators, one generator coupled to the gas turbine, the other generator coupled to the steam turbine. So you can have additional power or additional work from this combined cycle gas turbine. Right, heat recovery steam generator. You call the steam generator for the combined cycle as a heat recovery steam generator, HRSG. Okay, because of that, right, the efficiency is high, considered very high for a combined cycle gas turbine, approximately 50 to 60% efficiency. So you can imagine single gas turbine efficiency maybe around 30%. Coal-fired power plant efficiency maybe around 40%, right? The efficiency. Then when you have a combined cycle power plant, you can go up to 60% efficiency. Okay, and then for the combined cycle power plant, we use that primarily for intermediate, okay, intermediate load, or maybe in some cases they treat it as a base load. Okay, this is for combined cycle. Don't get confused between the open cycle. Open cycle, of course, we use that mainly for the peaking load. But for combined cycle, I would say the majority of time, we treat the combined cycle to be used in the intermediate or base load. Okay, this is an example of the combined cycle gas turbine. So you have a gas turbine at the top here, top figure here. At the bottom here, you have a steam turbine. Same thing, you have a compressor, compress the air into the combustion chamber. Air drive the gas turbine drive the generator. Okay, and then the hot exhaust gas, we channel that into a steam generator, heat recovery steam generator. Heat up water, drive the steam turbine. You have another generator here. So this is a simple illustration that describe the combined cycle gas turbine. Okay, you can also have a single shaft gas turbine. It means the turbine and also the generator, okay, they are having a single shaft, and then you can also have the multi-shaft steam, multi-shaft system. Okay, the main difference. Okay, let's have a look here. Okay, since we are talking about steam turbine, if you look at our previous slide here, you have a steam turbine in our combined cycle. So this is a steam turbine that we use in our combined cycle power plant. When we talk about steam turbine, we remember the steam turbine that we use in our coal-fired power plant. So there are two steam turbine there. One is a steam turbine used in the full coal-fired power plant. The other one is the steam turbine that we use in the combined cycle power plant. They are different. They are not the same class. They are not from the same size or category. So we look at that. The main difference between the conventional steam turbine. Conventional steam turbine that we are referring to the steam turbine, the standalone steam turbine that is used in the coal-fired power plant. And then you have a combined cycle steam turbine, which is used in the combined cycle power plant. So what are the difference? You look at the conventional steam turbine. Okay, steam turbine, the usual one, the conventional steam turbine, they have usually higher rating, higher power output. Okay, and then the steam temperature and pressure that drive the blade, that drive the turbine for conventional steam turbine is higher. Okay, and then the conventional steam turbine, it has higher number of steam extraction for the feed water heating. On the other hand, for the combined cycle steam turbine, okay, usually it has no bleed point. Bleed point means you don't tap the steam to be channeled into your regenerative system or to be channeled into your feed water heater. Okay, it is fewer or even no bleed point for steam extraction if you are referring to the steam turbine that we use in our combined cycle power plant. Okay, whereby if you look at the conventional steam turbine, the tapping point for heating up, if water heating, you can have 6 to 8 tapping point. They channel or they tap the hot water or the superheated steam from the steam turbine to heat out the feed water heating for the conventional steam turbine. For combined cycle, I would say none lah, none or even very very few lah kalau ada. Okay. For the combined cycle steam turbine, usually smaller, okay, floor mounted configuration. It has a shorter startup time for the steam turbine that we use in the combined cycle power plant. Okay, because of the size is small, they don't require steam at a very, very high temperature as what the conventional steam turbine require. And because of that, they have lower power output lah. Okay, lower power output, lower live steam pressure as compared to the conventional. The comparison is given here. Okay, if you look at the combined cycle power plant, the pressure is around 100 to 170 bar. If you look at the conventional steam power plant, the pressure can go up to 350 bar. So you can imagine the magnitude of pressure, okay, when you talk about steam turbine that we use in the conventional power plant. Okay. Right. We also use gas turbine in cogeneration. Okay, so we have, in summary, we have open cycle, we have combined cycle, we can also have a cogeneration plant. Okay, cogen plant use gas turbine as well. Okay, gas turbine used for production of electricity and process steam. Same thing, the one that we mentioned in the steam turbine. Okay, when you want to produce the steam, okay, of course, you are referring to, I mean, in that particular industry or in that particular factory, you have a gas turbine to produce the electricity. At the same time, okay, you have a steam turbine, okay, whereby the steam turbine is the non-condensing type. They use the steam to run their processes in that company lah. Mean that in other words, the gas turbine is used to produce the electricity. You have obtained the hot exhaust gas. The hot exhaust gas is used to heat up water. So water becomes steam. They use the steam, okay, as part of their process in the industry or in the factory. Okay, we call that a cogeneration plant. Okay, you can see here an illustration that describe the cogen plant, and as an example here. Okay, and then in terms of the thermodynamics of gas turbine, I think this is a repetition, the repetition from Brayton cycle that we have done back in the thermodynamics too. But it is important for you to, to know what are the processes that make up the Brayton cycle. Remember, Brayton cycle is a cycle that we use to model our gas turbine system. Okay, you have compression. Okay, compression in a compressor, isentropic condition, and then after the compression, you have combustion, heat addition. Okay, heat addition here at constant pressure. After that, you have expansion, okay, for your turbine. And finally, you have heat rejection. So this is a typical cycle for Brayton cycle. So now you have a Rankine cycle, the cycle that represent our steam turbine. And now we have Brayton cycle, okay, the cycle that represent the gas turbine cycle. Okay, in terms of efficiency, gas turbine is also a heat engine. So a heat engine efficiency is given by W up divided by QH, or you can also simplify that, okay, the efficiency in terms of 1 minus QL divided by QH. This is also a repetition. This is a typical efficiency of a heat engine. Okay, gas turbine is one of the examples. Steam turbine is also our example of a heat engine. This is based on the actual thermal efficiency. We can also estimate the efficiency of our gas turbine by using the approximation here, 1 minus 1 divided by P2 divided by P1 to the power of K minus 1 divided by K. K here is the specific heat constant. Okay, it depends on the gas. Usually for air, I think it's about 1.2. You can refer to the values of K from any handbook. So what we want to highlight here is that the efficiency of our gas turbine is only a function of pressure ratio. Okay, P2 divided by P1 is actually pressure ratio. Pressure of fresh air coming into the compressor, coming in at P1, coming out from the compressor at P2. So this equation simplify that our efficiency, I mean, if you know the pressure ratio of your gas turbine, we can estimate the efficiency of our gas turbine. So that is the simplification made lah for this. So typical pressure ratio P2 divided by P1 is around 11 to 15. This is typical pressure ratio for the operation of the gas turbine. We don't want to have our pressure ratio to be very, very high. Okay, when I talk about pressure ratio, just bear in mind, let's say fresh air coming into the compressor at 1 bar, 1 ATM, 1 bar, and then it comes out at 10 times higher pressure, 10 bar. So the pressure ratio is around 10. So that will be the approximate pressure ratio. Okay, pressure ratio also indicate how much work that you need to put in your compressor. Remember, in order for the compressor to work, we have to we have to supply some work. Okay, compressor is a work consuming device, not like a turbine. Turbine is a work producing device. Okay, for the compressor to work, you have to put in the energy. I mean, we have to supply the energy into the compressor. So if you want to have higher pressure ratio, of course, you have to put in more energy into your compressor to get to the higher pressure ratio. That's why it is no point for us to get the pressure ratio up to 50 or up to 100. Doesn't make any sense. Okay, if you look at this plot, this is the graph of efficiency, right? Efficiency of our gas turbine Brayton cycle against the pressure ratio. When you have a higher pressure ratio, okay, you can see the graph is already saturated. There's no more increase in the efficiency. So I think the optimum numbers or the optimum condition is around somewhere around here. That's why we say that the pressure ratio 11 to 15 is already optimum enough, okay, for you to increase your efficiency of your compression or efficiency of your Brayton cycle. All right. We refer back to our processes that we have in our Brayton cycle. Let's say this is a TS diagram, temperature against entropy diagram. We have two pressure. One is at the higher pressure. The other one is the lower pressure. 1 to 2 is a compression. Usually we assume it to be isentropic. 2 to 3 here is the heat addition process in the combustor. Okay, 3 to 4 is an expansion. Usually we assume it to be isentropic as well. And then 4 to 1 is the heat rejection. Q out happen here. Q in happen between 2 and 3. Right? Under ideal case scenario, of course, we assume 1 to 2 to be isentropic, 3 to 4 to be in isentropic as well. Okay, under ideal condition also we assume 2 to 3 heat addition, they occur at constant pressure. 4 to 1 also we assume it to be happening at constant pressure. But in reality, that is not possible lah, because we always have the losses. So that's why from 1 to 2 here, we have an increase in entropy, no more isentropic. 3 to 4 in the turbine, no more isentropic. And you might be having pressure drop lah. From 2 to 3, pressure is not constant in reality. 4 to 1 also, pressure is not constant. So we call that irreversibility. I think this is also, I mean, you have done this in thermo 1, thermo 1 or maybe thermo 2 as well. Now we have the term that we use to describe the amount of work that is contributed to your compressor. Okay, in the gas turbine, you have a compressor, you have a turbine, right? Compressor is a work-consuming device. Turbine is a work-producing device. So where does the work come from for the compressor? Okay, the work in the compressor is actually obtained from the work produced by the turbine. So let's say you're talking about turbine work here. Some of the turbine work is actually used to drive the compressor. Then the remaining is the one that is useful or that is converted into the electricity. So we call that the back work ratio. Back work ratio, the fraction of turbine work which is used to drive the compressor. So this is how it works lah. Because you have a work consuming device, you have a work producing device under the same machine. Work produced by the turbine is actually being used, some of it being used by the compressor in order to compress more air for the combustion process. So that's why if you are having a gas turbine during the startup too, okay, because when the turbine is ideal condition, you don't have any work produced by the turbine. Somehow to run the compressor, we have to use an external force. Okay, during the startup of a gas turbine, you have to use an external force to drive the compressor. After the engine has been running for some time, then only we can extract the power from the turbine, use it to drive the compressor, and then we can shut down all the external forces used to drive the compressor. Okay. Okay, let's go into the major component. Major component, the important component that we have in our gas turbine. This picture is an illustration of the gas turbine that we use for Siemens model. Okay, we don't have that many components. We have air intake. This is important component lah. Air intake for channeling the fresh air into the compressor. And then we have a compressor, right? We have a combustor, okay, for the combustion to happen. You have a turbine, and at the end here you have the exhaust ducting. So these are typical major component that we usually do the maintenance lah in the operation of power plant, gas turbine power plant. Okay, if you look at the GE model, all right, this is similar thing actually. You have an air inlet, you have a compressor here, all right, and then you have a combustion chamber. You have a turbine towards the end, and at the end here you have the exhaust ducting. So those are the important component. Now when we look at each of these components in detail in terms of the characteristics and in terms of how does it work. Okay, for the air intake here, it contains a large amount of air filter system. Okay, we know that when you want to drive or to suck the air from the atmosphere, the air has to be clean. Okay, otherwise it will damage the compressor blade. We don't want any dust. We don't want any impurities to come into your compressor. Otherwise, it will damage the compressor blade. That's why we have to have a good filtering system. Okay, it may include evaporative cooler, okay, to lower air inlet temperature. This is like a spray of water. Okay, they might be spraying water to the air inlet to cool down the temperature. Okay, why do we need to cool down the temperature, especially in Malaysia when you have the ambient which is high, the ambient condition which is high. Okay, when you have high inlet temperature, okay, the efficiency is actually going down. Okay, we need to lower down the air temperature, first of all, to increase the density. When you increase the density of air, you are actually bringing in much air as compared to the normal condition. Okay, you increase the mass flow rate, you increase the, I mean, when you have air, the amount of mass flow rate of air entering your compressor is high, then the burning rate is also high. At the end of the day, you are getting the higher turbine output. So that's why we usually try to lower down the temperature of air that goes into our compressor. So the equation energy balance for compressor W equals to M delta H in minus H out. This is also typical for a compressor. You have done this before. Okay, this is a picture of a typical air inlet. So you can see this is a huge air inlet. And because of that, you can imagine the amount of air filter that is needed, okay, to operate a gas turbine power plant. Okay, we require a large amount or huge amount of the air filter, and then this air filter needs to be maintained and replaced on a regular basis lah. Okay, this is another illustration of the air filter that we use in the gas turbine power plant. Okay, this is one of the example. You can have different configuration or different gas turbine or different design. They have different types of air filtration system, but the main function, they are the same. Okay, the next component, major component, okay, don't have to repeat that. The compressor, the compressor, as you know, the function is to compress, to draw in air and compress it. So compression, it happen in different stages. Okay, we cannot simply compress from 1 bar to 10 bar in one go. First, it is not possible. So the compression has to happen slowly lah. I mean, from 1 bar becomes 2 bar, from 2 bar become 3 bar, 4 bar, 5 bar, and until you obtain to the final pressure of 10 bar. That's why if you look at the configuration of a compressor, the compressor length is longer, okay, to accommodate the many stages of blade as compared to the gas turbine. Okay, as compared to the turbine stage, turbine stage is shorter as compared to the compressor. The only reason is that you have to compress the air slowly lah. You cannot simply jump from 1 bar to 10 bar in one go. That is not possible. Okay, in our compressor, we also have variable inlet guide vane to direct the flow, to control the airflow, and also to direct it into your blade. Okay, so that the angle is right for us to get the maximum rotation of our compressor blade. Okay, this is a figure that shows a compressor blade. You can see, okay, this is an example for a gas turbine. This is the compressor blade, and then towards the end here, you have a turbine blade. Turbine blade maybe 3 rows, or maybe compressor blade, they have like 8 rows or 10 rows of blade. So that is the reason you mentioned just now. The reason is you have to increase the pressure slowly. You cannot simply increase it suddenly, okay, up to the higher pressure. Right, then we have a combustor. This is where combustion happen. Okay, there are different types of combustor. You can have a silo. Okay, can have a multiple can or multiple cannula, and you can also have the annular ring. Silo is a large or maybe single silo or dual silo. The one that I show for the case of cement power plant or cement gas turbine. Multiple cannula is in the forms of small can, okay, small annular combustion chamber. And then for the annular ring is single chamber. You arrange that in the annular configuration. So we look at that later on. What do we have in our combustor? We have nozzle, you have air atomizer, you have a spark plug, you have an ignition system. We also have flame detector, which is need to control the flame length. Okay, you might also have steam or water injection system in your combustor. Okay, for the case, let's say for example, you are doing combustion and then suddenly you find out that temperature goes very, very high, 2500 as an example. So somehow we need to lower down that temperature, maybe to prevent the formation of NOx. So somehow we need to cool down the flame temperature. This is by injection of water or injection of steam into your system. Okay, right. This is a picture showing a silo type combustor. Okay, you can see here. This is the axis, right? This is the axial direction. Maybe compressor is located somewhere around here, and the turbine is up there. So you have silo. This is a silo. Maybe two silo, one on the left, the other one on the right. This is actually the combustor. Okay, and then you can have the cannula type. So it is made from smaller can here, arranged around the gas turbine axis. Okay, so different types of combustor, maybe they are having different pro and cons lah, different advantage or maybe some disadvantages, especially when they talk about big silo. Okay, when you have a big silo like this, you only have two combustor. So if one is not working, you have the other one. Okay, but if you have both not working, then somehow your gas turbine cannot be used anymore. As compared to the can type, you can have many. So if many not working, maybe half of it not working, you can still manage to get the combustion going. Okay, this is the burner. Okay, which is located inside the combustor. This is where fuel and air are injected into the system to get the combustion gas. Okay, then we have a turbine as the major component. Okay, for the turbine, the one that drives the turbine is actually the air, the hot exhaust gas. Expand through the turbine, it drives the turbine, so energy has been converted into that rotational movement. Okay, you might have a series of rotating and also stationary blade, just like a steam turbine, okay, for the gas turbine. It is written here, okay, for your information, that half of the work produced is actually used to drive the compressor. So you can imagine the amount of work consumed by the compressor is already half the total work produced by the gas turbine. Then you only have half. So that's why the efficiency for the open cycle is less than 50% because the majority of the power is used to drive the compressor. Okay, bear in mind also that the turbine work produced, okay, is also used to drive the other auxiliary, the subsystem, the smaller subsystem to support the operation of the gas turbine. For example, the lubrication oil and also the hydraulic pump. Okay, because you want to operate the pump and also hydraulic, they require work, and that work is actually tapped from the gas turbine. Okay, from the turbine just now. And then since the turbine is actually experiencing the hot exhaust gas, combustor contain the combustion gas. Combustion gas, it flows directly to the turbine. So the first stage of the blade for a turbine has to be strong enough, okay, to withstand the high temperature of the combustion gas. You can see the temperature can go up to 2000 Kelvin. So somehow 2000 degrees, 2000 Kelvin or 1700 degrees Celsius will be experienced by the first stage nozzle or first stage blade in our turbine. And because of that, there are special material needs to be constructed for the gas turbine, especially for the first stage or maybe second stage of the turbine. And then that particular blade, usually the blade, they come out with their own cooling system, okay, to ensure that it does not damage when hot exhaust gas flows through it. Okay, we will look at that later on. And then towards the end here, you have the exhaust. The exhaust gases are either released to the atmosphere for open cycle case, or it is being channeled to a boiler or heat recovery steam generator. So either you leave it to atmosphere, that is based on the open cycle, or you can also reuse that, that is based on the combined cycle. Okay, there
Yes, sir.
are, yeah,
You mentioned before that the open cycle with the intermediate and base. Can you explain it more?
can you repeat that?
Before this, you mentioned about intermediate and base regarding the open cycle.
Betul. Okay, intermediate load, usually we use the combined cycle. Okay, open cycle, usually we limit that to peaking load only during the peak, because open cycle, we don't have that many plant that operate on the open cycle, because open cycle, it is actually resulting in the loss lah, because you are releasing hot exhaust gas to the air. So we limit that to the peak load. Okay, for the combined cycle, yes, we use that to the intermediate load, or the, in some cases, maybe for the base load. That is for the combined cycle. We don't use open cycle for intermediate load. We use open cycle only for the peaking load.
Okay, thank you, sir.
Okay. Okay, when we talk about exhaust, you imagine you have a combined cycle power plant. Okay, maybe you can convert. I mean, this is a combined cycle power plant you are operating. Suddenly, let's say, for example, your steam turbine is not working. So you depend solely on the gas turbine. So the hot exhaust gas, somehow you need to release that to the chimney, to the atmosphere directly, because steam turbine not working, so we don't have to heat up the water anymore. So we have a channel, some kind like expansion joint to close or to open the hot exhaust gas from entering the heat recovery steam generator. We call that an expansion joint to allow for thermal expansion, or the exhaust plenum for the ducting. It means that the exhaust can be rechanneled directly to the chimney lah. Okay, in the case when your combined cycle power plant, your steam turbine is not working. So this is part of the design lah. Okay, this is the picture of our gas turbine. It is a combination of compressor and also a turbine. So you can see that kind of illustration lah. All right, this is the one that I want to highlight here. This is in terms of, okay, we mentioned that in a turbine, okay, the blade of your turbine, it will experience a very, very high temperature of the exhaust gas from the combustion chamber. Okay, when you talk about 1600 degrees Celsius, if you do not coat your turbine will, I mean, the blade will melt lah. Definitely it will melt. So somehow there are technology used to make sure that the first stage turbine blade is actually protected from the hot exhaust gas. So this is an example from PD power plant, the GE system, that our turbine stage here, they contain 3 stages: first stage, second stage, and also third stage. Okay, each of the stage two, it contain nozzle and also blade. Remember the function of the nozzle to accelerate the gas and also to direct your gas so that it hit your blade at the right angle for maximum rotation. So you have nozzle blade, and also nozzle blade. The one that will experience the highest temperature is the first stage blade, and therefore the construction of the blade is very important. Okay, the blade is actually made from special material. It is coated with ceramic, and at the same time, the construction of the blade, it contains a cooling hole. So you are talking about air coming from the inside here. It cools down the blade lah. Okay, immediately during the first stage expansion. This is a picture of a typical blade. Usually the first stage blade is short lah. Okay, because the energy is the maximum on the first blade. So you don't have to put in a longer blade because the energy conversion is much easier as compared to the third stage as an example. Okay, this is the one that the actual blade that I did some X-ray in terms of, to see the cooling hole. This is the illustration of the cooling hole. So you can see there are actually some kind of channel, okay, that allow the air to comes in. Okay, the air that comes in is actually coming through the compressor. Okay, remember the compressor compress the air. Okay, majority of the air that goes through the compressor, it will go through the combustor. Some of the air will channel through the core shaft, and then it enter the blade here just to cool down the blade, and then it will lift towards the back of the blade. We call that the trailing edge of the blade. So this is an X-ray illustration of the cooling hole for that particular blade. This is how we protect our first stage blade from melting lah, due to the hot combustion exhaust gas. Okay, this is the CFD simulation that I did, okay, to illustrate the blade in the nozzle. Nozzle, it exit the blade through the leading edge. This is the shape of the blade. All right, and then you have cooling hole inside. Okay, it exit through the front. Okay, when it comes out from the front here, and then you know that hot exhaust gas coming from the front, the air is actually going back, okay, through the leading edge, and then this air will automatically forms a layer on the blade to protect the nozzle lah, basically. So that is one of the technology that they use, okay, in terms of the cooling air for the nozzle, cooling air for the blade as well. Okay, this is another illustration for the turbine cooling system. Okay, you have cooling hole. At the same time, we also put in coating, coating for thermal barrier. And that's why the cost of the blade is very, very expensive. Okay, when you talk about cooling hole here, Okay, you can just imagine the manufacturing process involved in order to make one piece of this particular blade. Okay, you cannot simply do the machining because of the complexity of the cooling hole inside the blade. Okay, somehow it has to be properly casted. Okay. Okay, I think I'm not going to continue on the GT performance here. Yeah, the performance maybe we can proceed tomorrow lah. So I hope that you have gone through some of the animation. The animation is very much clearer lah in terms of to understand the principal operations of the gas turbine. Okay, I think we will stop until here, and then we can continue maybe tomorrow for the rest of the slide. Okay.
Okay, sir.
All right.
Alright, sir. Thank you.
Thank you.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.